Hi, this is Jayaraj. Sometimes we want to do machine learning or statistical computing. We want the comforts and convenience of a high-level syntax, but we want very low overheads, similar to that of C or C++. For example, we may be working under time constraints or memory constraints. For example, maybe we want our machine learning program to run in a small embedded device like Arduino or Raspberry Pi, or maybe we simply have severe time constraints. Now, languages like Python provides convenient high-level syntax, but they come with certain overheads associated with interpretation or dynamic memory allocation and so on. So here I've been toying with a domain-specific language where we can define machine learning pipelines or some kind of data processing pipelines. And the DSL provides a high-level syntax for defining these pipelines in a modular fashion and provides high-level syntax for vector matrix operations and has certain other interesting features we'll see shortly. So this is, so let me walk you through a simple program in this DSL. So the main module in this, in the DSL, so usually, for example, in C or C++, the main module contains a main function, right? So here the main module defines a pipeline as a, so the DSL has a Python-like syntax, and I've named the DSL MotePy. Mode because it's meant for resource constraint situations, and Pi because it has a Python-like syntax. So the main module defines a pipeline, the data processing pipeline, as a Python-like list of operations. So the first operation is data source.acquire, then second operation model.predict. So here data source is a module and acquire is a function in that module. Model is another module and predict is a function in the module. So let's go to the data source module. So as you can see, the syntax is Python-like, but it's not Python because the language is statically typed and a static memory allocation, so there is no dynamic allocation. As you can see, so every module has an init function and it can have any number of other functions. But one particular function is called a flow function. This is the one which gets invoked as part of the pipeline execution. So in this particular case, acquire is as defined as flow function using this decorator. And here, I'm just randomly allocating, assigning some values to this data array or vector. And then I'm invoking, so the next, so when we want to invoke the next module in the pipeline, so from within a flow function we call the next with the data for the next module. So this is kind of, so without hard coding a call to the next module, we can actually make a call to the next module like this. And the wiring is done in the pipeline module. So that's what this data source does. So it randomly initializes the data and then pass it on to the next module. And next module here is predict, model.predict, and here model this implements something similar to a neural network, which has two layers. So first layer, just a bunch of weights. Floating point weights, and so there are two layers. And here again I'm randomly initializing. I could read it from a file as well. So we are just, so init is randomly initializing the weights. And you can see here, so the vector matrix operation, there is direct syntactic support for that. So I'm just doing a regular multiplication here. So that gets converted into vector matrix operation by the DSL compiler. And here is a second vector operation. So and this results in a single floating point value. We could apply an exponential function or something to this, and we are just printing the result. So let me just compile it. So there is a shell script for compilation, which invokes the necessary processing stages in the compilation. And for the compiler, we pass the main pipeline module, and we can ignore the warnings. So you can see it has generated two files, out.cc. So the compiler converts the DSL into low-level C++ code, which is then compiled using a C++ compiler. So if I it prints the result. So the pipeline is executed. So there is an implicit loop here. So it is continuously executed. And if you want to limit the number of iterations, we can just pass 10, then it will execute, do 10 iterations. So let's just briefly look at this generated code. So you can see, there is a loop, and so it has generated some low-level code corresponding to the high-level code. Like for example, the vector matrix operations, it has converted into loops and generated the right code for vector matrix operations. Now let's look at another small example. So here is another pipeline. There are two stages: stage 1.process and stage 2.process. And here, so stage 1, does some, it has a vector. It initializes a vector, then does some processing with it. And here I am printing the address of the vector. So we can mix the C++ code freely with this DSL. And interesting thing is the vector layout and matrix layout of this DSL is exactly compatible with C and C++. So there is no need for any foreign function interface or calling convention or anything like that. So here there is no parameter, so we are just calling next. And the process, then the next module also initialize. So it has two vectors. Initializes one vector, does some processing. Initializes the next vector, does some processing. And vector 2's, vector 3's address is also printed. So let's look at something interesting. Let me just go to this. So let me compile the module, and so you can. So let me just execute it once. You can see that all the addresses are same. So although there are three vectors, addresses are same. That is because although there is no dynamic memory allocation, the compiler is intelligent, and compiler tracks the lifetime of these variables, and then it knows that the lifetime of this, for example, this variable, it gets initialized here, right? So whatever data was previously there in this vector is no longer used after this. So the lifetime of this variable is only this segment of the program, and lifetime of this variable is only this segment of the program. Lifetime of this variable is only this segment. So this one is this segment, and this is this segment. So because these lifetimes are non-overlapping, it reuses the memory addresses. And I'm calling this compiler managed heap. So normally a compiler that does static allocation, like in any language like C or C++, it do not reuse memory. It cannot track lifetimes. Of course, one reason why it is simplified in my case is because I have an explicit pipeline structure here. And now here, now let's say I don't initialize it here. Let's say I initialize it here and I reuse the old values. Let's see what happens. So let me just compile it. So here you can see that, so in the previous case, all the addresses were same. But here you can see that vector 1 now has a different address, and vector 2, vector 3 still has same address. This is because compiler now knows that vector 1 data's lifetime is throughout the entire pipeline, because it uses the old values to compute the new values. Whereas vector 2, vector 3 still can be reused. So it knows, it intelligently tracks the lifetime of variables and then reuses. So this is a novel concept which I'm calling compiler managed heap. So this combination of compiler managed heap and high level syntax for vector matrix operations make this a good candidate for performing machine learning and statistical computing and data processing operations in resource constraint or time constraint situations. And I will be doing some example projects using this in the coming months. Thank you.